Hello everybody, welcome. Today we're gonna be doing the wind load analysis on a roof truss, and today we're gonna design the loads, and then we're gonna design the purlin right here first, and then so on. Okay, this is the design of roof truss. Number one is purlin. Number two is roof truss structural member. Number one, purlin. Two is the top chord. Three is the bottom chord, and the bolts for connections, and the details. There's some of the details right here. This is the cross section of the roof. The roof is inclining 16 degrees. Here are the dimensions of the wood that is used in the roof. The rafters 2x6, purlin is 2x3, it's a 0.7 on center with 2x2 wood clit. This is the wood clit, okay, making it stronger so it doesn't move. This is the flashing, and this is the dimension of the clear span of the roof truss is 5 meter, and I show 3 purlins in here so I can illustrate the tributary area of one purlin. We're just gonna design one, and all of them they're the same. Alright, so tributary area is the distance between this line is occupied by the tributary area, the area that carried by the purlins. This is half of this distance here and half of that distance here. I illustrated right here. Clear illustration is right here. The tributary area, these are the rafters, and these are the purlins. Here's the tributary area that's gonna be carrying the load and applied to the purlin. Half of this distance between, which is 0.7, and half of this. And to solve for the tributary area is you add these two hubs. For sure it's 0.7, and then multiply it by the length. That is the total tributary area carried by the purlin, and that is where the load is calculated, okay, through the tributary area of the purlin. Now in this project I use the corrugated roofing. It's a corrugated GI sheet, and the gauge for this thickness is described as gauge. This is gauge 26, and the weight for the total weight of the roofing is 11.14 kilogram. And here are dimensions: 1.3 there, and the length is 2.7. the length, this is typical, okay, and the length is, it has different lengths, commercial lengths. I choose 2.7. this is 9 feet. You convert this based on the dimension of the roof truss. When you choose this, you gotta look at your dimension first, and then figure out what size of the GI corrugated sheet you can use. Okay, this particular project is suit for 2.7 the length. Okay, the maximum length for the GI is 12 feet. It's 3.6 meter. So this is the total load, total weight of the one piece of GI corrugated sheet. 11.14. We gotta figure out, we gotta solve for the weight every square meter of one piece. Okay, so area of one piece GI roofing is 0.13, and times 2.7 equals to 3.51 square meter. Now the weight of roofing per square meter, we gotta solve for every square meter. It's 11.14 divided by the total area, so we get the per square meter. It's 3.2 kilogram per square meter. Here are the solutions for the how to calculate the loads and find the load normal to the roof. PN is the normal. Okay, that's the load we're looking for when you design a roof truss. A roof truss, especially the purlin and the top cord. Now, wind pressure. The roof is known to carry a wind pressure, and the wind pressure the dynamic pressure is the product of the velocity of the wind. This is the PDW is the dynamic pressure due to the wind. It is the product of the velocity of the wind and the theoretical weight of the wind itself, so that without the speed of the wind, the theoretical weight of the wind is zero. Okay, here's the theoretical illustration of the dynamic pressure. It's like in 1 cube there, 1 cubic meter. It has the wind inside that cube there is calculated to be 1.2 kilogram per cubic meter, and this is the speed of the wind pushing it to become a magnitude of a load when it's applied to a tributary area. But when there's no speed, this weight here is zero because it's not moving. Alright, this is nothing. So because of the speed of the wind, you get the dynamic pressure, and the dynamic pressure is calculated in the formula given below. It's PdW is equal to 1/2 times 1.2 kilogram per cubic meter divided by multiplied by the velocity square. The velocity square here in units is in meter per second, and the velocity that I choose to design the purlin and the whole roof structure is 250 kilometers an hour. In part of the world that is rainy and sunny and there's typhoon, a strong wind like this, usually it goes over here. It goes over 350 kilometers an hour. So I just designed this to it's in between 250 kilometers an hour. Alright, so the velocity, so that's kilometers an hour. We gotta convert this to meter per second, so we can apply this. We can use this formula to get the dynamic pressure. Okay, converting now. The design velocity of the wind is 250 kilometers per hour. Converting velocity to meter per second. This is the factor. You can a shortcut method. You can multiply 2 kilometers per hour. If you multiply this factor, you get that. The result is meter per second. But in details, it is like this: kilometers per hour multiplied by the hour over in 1 hour there are 3,600 seconds, and multiply again by in 1 kilometer there are 1,000 meters. Okay, so that kilometer will cancel. You put the 1,000 on top, kilometer cancelled, 1,000 meter for 1 kilometer, cancel kilometer, hour cancel. What you left is 3,600 seconds, 1,000 meter, so it is meter per second. Okay, so 1,000 you divide it by 3,600, you get this factor here. For shortcut method, multiply that kilometers per hour by 0.27777, you get meter per second. So that's how we convert that. So converting that, we get 69.44 meter per second, the equivalent of 200 kilometers per hour is 69 point. And now, since we have this, we can apply this to the formula in equation 1, which is the PdW, so that we can get the dynamic pressure of the wind. So substitute that value in the velocity square there and solve all this together. You got 1/2 times 1.2 times 69.44 square. You square this 69.44, you get 2,893. This is newtons. Okay, the result of this formula here is newton per square meter, and we still have we need a kilonewton. We still have to change it to kilonewton. All we gotta do is divide it by 1000. You get 2.89 kilonewton per square meter. That's the dynamic pressure, and this dynamic pressure is in square meter. If you multiply this by the total area of the tributary area, you get the total, that is the total load, the magnitude of the load due to the wind pressure. Here's the total load due to the wind load, normal to the roof. We need the wind pressure is horizontal load. Okay, the winds is always horizontal, and it is horizontal and it's parallel to the ground. Okay, your reference is the ground, it is parallel. Your reference to solve for the PN is always the ground line, which is 180 degrees. So this is the wind load. We need that load normal to the roof. Any load, the wind load is considered to be an inclined load. Any load, any position of the load applied to the inclined surface. The roof is the inclined surface. Any load applied to the inclined surface is considered to be an inclined load. Okay, the wind load becomes an inclined load by analysis because it is applied to the inclined surface, which is the roof. This is the explanation of why the horizontal load or any load applied to the inclined surface is considered an inclined load. See, this is 16 degrees with respect to the ground line, right? So if you position the roof parallel to the ground in horizontal position, carrying the load there with the wind load, this is what happened. Look, the wind load is right here. Now the roof, I rotated it at 16 degrees parallel to the ground. This is like the ground now. Carrying the load, what happened to the load? Any loads there, when this is inclining, any inclined surface, any load is an inclined load. So this is what happened. See, the wind load now is an inclined load. When you rotate this roof truss parallel to the ground, 16 degrees, rotate parallel to the ground. See, horizontal position of the roof. That's the horizontal position. This is the wind load now, 16 degrees. See, the PN is 90 degrees with respect to the roof. This is the roof line. So this is what we're looking for, that load there. The inclined load is, any inclined load has to be resolved with the two components of load, one horizontal and one vertical. We're looking for the vertical load at 90 degrees with respect to the surface that the load is applied for. Okay, the horizontal will not affect to the roof because it is parallel to the roof. So we're looking for PN due to the wind load. Alright, so that's 16 degrees. So that's the explanation there why incline any loads applied to an inclined surface will be considered and analyzed as the inclined load. And when the inclined load is applied, you have to resolve it in two components of load, one horizontal and one vertical. It is the vertical load, 90 degrees with respect to the surface where the load is applied for, and that's the load that we're looking for to solve the load due to the wind. Okay, we're done with that dynamic pressure, and we are here. So that's the PN, the W right there, the wind load, 16 degrees. These three lines here, the ground is always the reference for wind loads. Okay, the ground, the top chord, and the wind loads, they are in the same horizontal plane, three of them. Okay, and since they are in the same horizontal plane, if this is 16 degrees, for sure this angle here is also 16 degrees. This is the angle where inside the vertical and the horizontal component of the wind load, and that is the angle of the load that we're gonna use to solve for PN. Alright, 16 degrees. That's easy. The dead load is a little bit difficult than the wind load to find the normal load due to the wind load. See, this is the right here. See, that's the dead load. This is gravity load going down to the ground. Okay, now this is the wind load, and this is how the winds apply to the roof. This is a corrugated sheet, and underneath that is the purlins, and this is the tributary area carried by the purlin. Each purlin has a tributary area, has its individual load. So this is how you calculate the load for one purlin. Okay, you need a tributary area. And since the roofing is obviously a uniformly distributed load, the purlin also is uniform load. It's not a concentrated load. Concentrated load is different than uniformly distributed load. It has different shear. The shear for uniformly distributed load, its distance, this is shear load, and it's small than one total load applied to the purlin. That will shear off right there in the middle. That's great. So this is kind of good, uniformly distributed load. Even the purlin itself is 3.6 meter. It's uniform. So we after the uniformly distributed load. There's no concentrated load in the roofing. Alright, PN. PN is we're gonna use 16 degrees. The PN, if this is the angle here, the PN side is the opposite side of 16 degrees. Okay, in this angle here, that's the opposite side, which is 90 degrees right here. This is the opposite side. And the wind load, we know the value of that wind load. The wind load is the hypotenuse of 16 degrees. And since this is involving the opposite side and the hypotenuse, we can use the trigonometric function of a sine. A sine is opposite over hypotenuse, right? So we use that trigonometric function of a sine. So sine 16 degrees opposite over hypotenuse. So PN is the opposite, and the hypotenuse is the wind load. So manipulate that. If to solve for PN, we gotta cross multiply this equation here. PN equals to sine 16 degrees times the wind load. So it's the value for sine 16 degrees is 0.7564 times that wind load 2.25 kilonewton per meter. PN finally is 0.62 kilonewton. Okay, that's the PN. Now we got the PN value there. Okay, that's the final load applied to due to the wind load applied to the purlin. Alright, so this is it now. The PN right here. PN due to the wind load that's the load gonna be using to design the purlin. Okay, now the load due to dead load and live loads, normal to the roof. The load due to the dead load and live loads, normal to the roof. We after put the normal to the roof, right? Okay, live load is 2 kilonewton per meter. Roofing, we solved that earlier, is 2.0203 kilonewton per meter. The sum of these two, the purlin and the roofing, is 0.034 kilonewton per meter. The total dead load plus live load, 2 kilonewton per meter plus 0.034. We get the total dead load plus live load is 2.034 kilonewton per meter. So solving for the normal dead load and live load, this is the PN. The load PN means the load normal to the roof, to the surface of the roof, and this is the category of dead load and the live load. So it's a little tricky to solve for this angle here. We're looking for, this is the dead load and live load. The dead load and live load is gravity load and the direction of their weight. Okay, the direction of their weight is going to the ground, 90 degrees to the ground. That's why I illustrate this. Always refer to the ground when you solve for analyze roof loading. Okay, this is 90 degrees. This is a gravity load, and therefore the weight is directed going to the ground, and it is 90 degrees, analyzed at 90 degrees to the ground. So this is your ground. This is the dead load and live load. This angle here is see here is 90 degrees. The roof is inclining 16 degrees. Okay, I'm there, 16 degrees, and the PN DL is 90 degrees with respect to the roof. Okay, that's 90 degrees. Alright, we're gonna solve for B so that we can subtract it to the D, and the solution is right here. A is 16, C is 90, and B, the angle B here, angle B is 90, which is the C right here. P minus this A here, what's remain there? What's left? That's 74 degrees. Okay, to the roof line. That's 72 degrees to the roof line. Now the PN is 90 degrees to the roof line. So they're overlapping there. So 90, this is 90 degrees, and minus that B angle there, 74. Therefore theta is 90 is D, this angle D to the PN. Only one goes to the PN, to the roof, to the line of the roof. So theta is D minus B. Minus 74 is again equal to 16 degrees. It's always like that, but I have to show you the solution why this is. And what is the angle of theta? We need an angle here to solve for PN. This horizontal component here, this is again this load applied to the inclined surface. Again, this has to be resolved to the horizontal and vertical component. The horizontal right here is parallel to the roof, and this is the vertical component of the dead load and the live load. Okay, this is different than the wind load. Okay, the angle theta there is 16 degrees according to our solution right here, and it's resolved right here. Okay, this is the illustration, so we can look at it and solve for the PN due to dead load and live load. This is the adjacent side of the angle, because this is the 90 degrees, right? The adjacent side right here, the hypotenuse right here, and this is the opposite side. So we're looking for this the PN right here, the adjacent. This is the adjacent side now of the triangle. So we're looking for this, and since this involves adjacent and the hypotenuse of a triangle, and what is that in trigonometric function? The adjacent divided by the hypotenuse, there is a cosine. This time now is a cosine. So cosine 16 degrees is adjacent over hypotenuse. We can solve for Pn due to the dead load. So total dead load, live load 2.034 kilonewton, and use the trigonometric function of cosine. Cosine 16 degrees is adjacent over hypotenuse. Cosine 16 degrees now is called, substitute the value instead of this adjacent and hypotenuse there, Pn dl over dl. We're looking for Pn, okay? Pn dash dl now, due to the dead load and live load, is equal to cosine 16 degrees times the dead load and live load. We know the value of this, so therefore Pn is cosine 16 times 2.034. Pn due to dead load and live load now is equal to 1.955 kilonewton meter. Alright, so we solve, that's easy solve. So we have the Pn due to dead load and live load, and we have the wind load. So, and then you're gonna make a summary of the loads right here. Summary of all loads carried by the purlin. Okay, the dead load plus the live load and the dead load combined. We combined it here. Is a 1.955 kilonewton. Okay, this is, and the dead load is coming from roofing and the purlin, and the wind load itself is 0.62 kilonewton per meter. To solve that, let me see, 1.955 is equal to final 2.575 kilonewton per meter. Okay, 2.575 kilonewton per meter. I'm gonna go back there. You're gonna apply it here to the purlin, and this is the individual load. This is for the purlin, and this is for the roofing. You can have it here, roofing, see that, 0.0203, the uniformly distributed load, and the purlin is 0.0136, and the final load of the purlin is 2.575 kilonewton per meter. So that's the purlin now we're gonna design. Alright, and immediately I will do the design of the purlin following this video. This is it's not gonna fit in one video. There are probably 3 videos for this, but we have the longest part of the design is the calculation of loads, like this one what we're doing.